Welcome to Friday. All right, you two, any questions on the algebra review?
I have none.
All right, I will call off the even ones. Here we go. Number 2, 625. Number 4, 1 over 8. Number 6, 9 over 4. Number 8 is 1. Number 10 is -1. Number 12 is 54. Number 14 is 1 over x to the third power. Number 16 is 1 over t to the second power. Number 18 is 1 over x to the fourth power. Number 20 is s to the 15th. Number 22 is -12 x to the fourth, y to the third. And the last one is 8s squared t squared. And that's it. All right, we'll do 13.3 today. Oh, this is a good class. And then, as you can see, I'm not sure why I didn't highlight Chapter 13 test. I've said it a bunch of times this week already. We'll finish up with the Chapter 13 test, and the week right after this is the week before semester finals. So we'll get a couple sections into Chapter 14, and then we'll start Wednesday, Thursday, and Friday of that week. We'll start for the semester final review.
Life on it has had.
I think your computer's hacked.
It must be Ben's.
Yeah, sorry, I didn't realize. Hi, I'm here now.
All right. Here's your homework for tonight. Five 37, 538, 1 through 10 all, and 15 through 18 all. All right, fairly quick class. We'll spend some time on the classroom exercises. The proofs are very hard, but man, are they cool. I'm going to walk you through the proofs. They're pretty challenging, but boy, are they cool. All together, though, don't panic. It's a pretty easy day. So we're going to do a bunch of proofs today. Let's do some proofs. Chapter 13 is called coordinate geometry. And what that really means is that the shape that we'll be dealing with will be placed somewhere on the coordinate plane. And that placement is going to allow us to make conclusions or investigate some things about it. And it's also how we're going to do the proofs. We're going to take a shape and place it on the coordinate plane. And the mere act of placing it on the coordinate plane leads to the answers. All right, so we're going to start. All three of these that we'll do today are really slick, but this one's extremely slick. All right, we have been using this basic idea since 8th grade, the fact that if two lines have the same slope, that they are parallel. Now, we kind of just threw that out both in pre-algebra, algebra 1. We never proved it. Once again, we're in geometry, so we have to prove this, and we'll prove it right now. How they choose to prove it, this is a pretty challenging thing, because how do you prove that two lines are parallel? Well, the definition of parallel lines are two lines that never intersect. Well, how do you prove that two lines never intersect? I mean, we'd have to literally look at every single point and show that they are equidistant at every single point along both lines. That sounds near impossible. So the way that they choose to prove it is, well, coordinate geometry. They take two lines and they place those two lines on the coordinate plane, and somehow that mere act of placing those two lines on the coordinate plane allows us to do the proof, and well, that's what this one's about. All right, so we're given two lines, L1, L2. We're told that they have the same slope. Both of them have the same slope. But somehow we got to prove that they're parallel. And like I said, that's a challenging thing, that they're parallel. Well, you're going to see that it actually absolutely isn't that challenging, but the way they do it is pretty slick. I also want you to note that they already labeled angle 1 and angle 2. You see it labeled there on the screen. All right, so how do they do this? Well, obviously we have the beginning, we got the end, and here's the slick part. Because we've placed both of those lines on the coordinate plane, we get something from that. One, the fact that you have an x-axis and a y-axis. The y-axis is vertical, and the x-axis is horizontal. All right, so slope 1 is equal to slope 2. So the first thing they do is it's high school geometry. They make a couple triangles. So check out what they do. They say construct two congruent segments, one called AB and one called CD. And then they place AB and CD so that they both touch the x-axis and they intersect line 1 and line 2. So there's AB. I mean, I don't know specifically where it intersects, but certainly it intersects. And by the way, when we construct it that way, when we make it perpendicular, we've now made a right triangle. They take another congruent segment, CD, and do exactly the same thing. So I've made two right triangles. We can't tell much about the right triangles. Maybe they are congruent, maybe they're not. We're not sure. But they're certainly similar. I've got an angle similarity there, but we don't know if they're congruent. We just simply know that A, B, and C, D are congruent. But the other parts, we're not sure. And by the way, we probably should name the other parts. If we have a right triangle where line L1 intersects the x-axis and where line 2 intersects the x-axis, let's give them some names. We'll just label them E and F. Okay, so now we have two right triangles. Well, kind of a loss of what to do now, except that how do you prove that two things are parallel? Well, if we could somehow show that angle 1 and angle 2 are congruent, well, life would be good. Now, the way they go about showing that angle 1 and angle 2 are congruent is a little convoluted. So here's what they do. Well, the only thing we have to go on now is that we have two right triangles and that the slopes of L1 and L2 are congruent. So what do? They reached back to the given. The given says that the two slopes are equal to each other, so they define the slopes. Remember, slope is defined as rise over run. So if I look at the triangle there on the left, triangle AEB, we can see that the rise would be the distance of segment AB, and the run would be the distance of EB, and that would be the slope of that line. The slope of L2, right, line 2 would be CD would be its rise, and FD would be its run. Now, why can I say they're equal? Well, that's the given. The given says that they're equal. So I get this ratio of AB over EB is equal to CD over FD just from the fact that we are given that their slopes are equal. So by the definition of slope, rise over run, and the given, I get that proportion right there. Okay, so let's back up. What am I trying to show? I'm trying to show that angle 1 and angle 2 are congruent. If I can show that angle 1 and angle 2 are congruent, then by a theorem way back chapter 3 or chapter 4 that said that if two lines are cut by a transversal, that would be the x-axis in line 1 and line 2, that if two lines are cut by a transversal and corresponding angles are congruent, 1 and 2 would be corresponding, well, then the two lines must be parallel. So that's what I'm going to do. But I got to somehow show that angle 1 and angle 2 are congruent. So luckily, it's the end of the book for the geometry book. So we have lots of things that we can use. We're going to call on our friend trig. So trig allows me to say the next statement. If I think about, and I'm just choosing tangent, I could choose any one of them. If I just choose tangent of angle 1, remember SOHCAHTOA, the tangent of angle 1, suspiciously, I'm specifically choosing tangent, is also equal to that same proportion. Think about that. The tangent of angle 1 would be the rise over the run, except we don't call it rise over run, we call it opposite over adjacent. Check it out. Tangent of angle 1 would be equal to AB over EB. And the tangent of angle 2 would be CD. It's the same proportion. Now, since in that previous, that's definition of tangent. since in that previous statement we said that those two ratios were equal to each other, the only way that would happen is if tan 1 is equal to tan 2. You can either call it substitution, right? Or you could call it the definition of congruence. Either one's fine. But angle 1 must equal angle 2. Why? Because the tangent of 1 is equal to that ratio, AB over EB. The tangent of 2 is equal to CD over FD. In the previous statement, we said that those two ratios are equal. Well, you can't take the tangent of angle 1 and the tangent of angle 2, have them equal to that proportion, and the angles are not congruent. The only way that happens is if the angles are congruent. So therefore, angle 1 is congruent to angle 2, and we can conclude why, because remember, if you have corresponding angles and the corresponding angles are congruent, that only happens when the lines are parallel. That is crazy slick what they did right there. Notice we had a near impossible thing to do, which was to prove that two lines are parallel. Well, one way to do it would be show an infinite number of points on one line or equidistance to an infinite number of points on the other line, and that would require infinity to do. And we don't have that much time. So coordinate geometry allowed us to get to this answer. Pretty slick. Let's see if we can prove the converse of that statement. So let's see, originally we had the two slopes were equal. We proved that two lines are parallel. So the converse of that would be if they are parallel, are their slopes equal? Well, let's see if we can do that one. The proof is done in basically the similar manner. So we start off with the fact that the two are parallel, and then we construct those two right triangles again. If they are parallel, we can immediately also jump to the fact that angle 1 must be congruent to angle 2, because they would be corresponding angles cut by that transversal x. And then we can make those two right triangles the same method. I'll still say, point E and point F. And then we're going to just kind of do it in reverse process. So how do we show that their slopes are equal? Well, we need to show that the rise over run of one of those is equal to the rise over run of the other. And how we're going to do that is we're just going to call up tangent again, because tangent is the opposite of the adjacent, which would be the rise over the run of a right triangle. Okay, so let's see what we got here. Tangent of angle 1 would be AB over EB, and tangent of angle 2. I mean, this is just by definition of what tangent is. Okay, but we already know that angle 1 is congruent to angle 2, so therefore those two ratios must be equal to each other. And if those two ratios are equal to each other, therefore their slopes are equal. That's the definition of slope, rise over run. And there we go. That was pretty crazy. So we just proved one direction and we proved the second direction. So we proved a biconditional statement. And that's theorem 13.3, which basically says that if two lines are parallel, then their slopes are equal, and the opposite, the converse, that if two slopes are equal, then the lines are parallel. Now, to say as an if and only if statement, we say two non-vertical lines are parallel if and only if their slopes are equal. Now, why does it have to be vertical or non-vertical? Well, remember, the slope of a non-vertical line is undefined. So therefore, we couldn't say that, couldn't use an equality because we don't have a number. If the slope is undefined, well, I don't have a number equal to another number. All right, so that's theorem 13.3, something that we already knew, but now we've proven. So therefore, we can use it. Tonight for homework, what will they have? They'll have questions simply that say, we have two lines or two sides of a shape. You have the slope of one. What's the slope of the other? Well, if they're parallel, then their slopes are equal. And if their slopes are equal, then the two sides or the two lines are parallel. You'll see when you open up homework, they'll probably have like a rectangle or a parallelogram. And the only way you'll be able to prove that it is a rectangle or parallelogram is to show that opposite sides are parallel. How do you do that? Well, calculate both slopes. If both slopes are equal to each other, well, then those two sides are parallel. Okay, we good to move on?
Yes.
Yes.
All right, I said we were gonna do 3 proofs. We only got 1 more left. So we just talked about parallel lines. Let's talk about perpendicular lines. Now, this is something that we already knew from Algebra 1, that if 2 lines are perpendicular, if you take their 2 slopes and multiply them together, you get to this magic number, -1. Now, you probably remember this from last year, is that the slopes of perpendicular lines are opposite reciprocals. Well, if you multiply opposite reciprocals, you always get -1. All right, so let's see what we got to prove here. We have 2 perpendicular lines. Remember that by definition, that means they form right angles. We've got the slope of line 1 is we're going to call M1, and the slope of line 2 we're going to call M2. And somehow we need to prove that if you multiply the 2 slopes together, we get -1. Once again, a seemingly impossible thing to do since there's no numbers here. Literally, there's no number involved whatsoever here. I don't know any of their slopes. All right. So how are we going to do this? Well, it's coordinate geometry. We throw the picture on the coordinate plane, and from the mere fact that you've thrown it on something that has an x and a y axis, we can make some statements about it. So let's see what we can say. The first thing is I'm going to make another right triangle. So from where the 2 lines intersect, I'm going to drop a line down to the x-axis. I'm going to call it V. That vertical line there says construct V. That's vertical line. You read as such that. So construct V such that V is perpendicular to the x-axis, and then label sides U and W. So I'm just dropping a line straight down to the x-axis, the blue dotted line. I'm going to call that V. And by the way, we're talking about distances there, not the name of it, but that's a distance of V. And then therefore, the other 2 parts of the x-axis, we're going to label U and W. And remember, those are all distances. Okay, cool. And that's just basic construction. Now, I forget if it was chapter 5 or chapter 6. Way back then, we've seen this before. We have a bunch of corollaries about this. If you have a right triangle and you drop a perpendicular through the right angle of the original right triangle, you get 3 triangles, a small one, a medium one, and the big one. And we know that all 3 of those triangles are similar to each other, and therefore we can set up their sides in a proportion. And you're not going to see why I'm doing this until the very end, but I could make some statements. I'm going to choose one specific statement. Notice that I've got U over V. So if we look at the smallest triangle there that I made, notice I'm going short side over medium side. U is the short side, V is the medium side. The unnamed side is the hypotenuse. So I've got short over medium. So any other, either the large triangle or the medium triangle, I got to keep that pattern. So short over medium. So on the medium triangle, the short side is V and the medium side is W. So that's why it says U over V is equal to V over W. If you forget, this was chapter 8. This is corollary 1 to theorem 8-1. And that was a while ago. All right, cool. Why am I doing this? Boy, is this one slick. Boy, is this one slick. Why am I doing that? Well, let's now define the slopes of each line. Notice for each line, both L1 and L2, well, remember, all we need are 2 points, and where the 2 lines intersect are 1 point, and where the red line intersects the x-axis is another point. And notice, now I have the rise and the run for both lines. For line L1, notice the rise would be V and the run would be U. So M1, or the slope of line 1, would be V over U. Now, line 2 is, you got to be a little bit careful. We can tell simply by observation, by examination, looking at it, that the slope would be negative. So even though the distance for line 2 for the rise is V, we know we will be going in a negative direction. So the answer, the distance is always positive, but we know the slope would be negative. So the slope would be negative V over W. Think about it, rise over run. We will be dropping down and then going to the right. For line 1, we're going upward direction and to the right. So therefore, that's why that one is positive. Okay, cool. Well, that's just the definition of slope. Well, what good did that do us? Did that get us any? Somehow we got to get to, oh, wait, look. It says M1 is equal to V over U and M2 is equal to negative V over W. And at the very bottom here, it says, hey, all you need to do is multiply those two together. So let's multiply those two together, M1 and M2. So all I do is take those two equations, multiply them together. And we don't get a -1. We get what? Negative V squared over UW. Well, hold on for a second. And I'll show you the slickest part of the entire proof. The slickest part of the entire proof is, I'm going to have to illustrate this for you, is they take this right here and they look back to this statement right here. Well, this statement right here says UV is equal to VW. Well, this says negative VW. So by the property of -1, we know that negative VW would be equal to negative. All I'm doing is multiplying both sides by -1. So I could do for this part right here, I could do a substitution. And instead of writing negative V over W, I could instead write negative U over B. I hope you followed that logic. So that's what I'm going to do right there. All I did was a quick substitution, right? And the property of -1, right? Why did you do that? Well, look what happens. A whole bunch of things start to cancel. Well, the V's cancel, the U's cancel, and you're just left with -1. Oh, man, is that slick. So we just proved the fact that I never told you this in 7th grade, but in 8th grade in Algebra 1, we did have that when the two lines are perpendicular, that their slopes are opposite reciprocals of one another. In other words, if you multiply the two slopes together, you get to -1. And this is our last theorem of the day, Theorem 13.4. Theorem 13.4. This is an if and only if statement as well, too. I only chose to prove one side of it. In classroom exercises, they prove the other side of it. So they prove that if M1 times M2 is equal to -1, then the two lines are perpendicular. Okay. In Algebra 1, we focused on opposite reciprocals. In geometry, they focus on the fact that if you multiply the two slopes together, you get to -1. Either one is fine, but I will tell you it's more useful to remember opposite reciprocals than it is to remember that the two multiplied together is -1. Tonight for homework, they will give you one line and you'll say the other line is perpendicular to it. They'll say, what's the slope of the other line? You calculate the slope of the first line, and then you simply find the opposite reciprocal of the other one. Remember, to find opposite reciprocal, well, you take the opposite of the number and then you flip the fraction. If it's not a fraction, you make it a fraction. That's how you make an opposite reciprocal. If it's negative, it becomes positive. If it's positive, it becomes negative. That's the opposite part. The reciprocal is, well, you take the fraction, the original fraction, you flip it. If it's not a fraction to begin with, you put it over 1 and then you flip it. Okay, we all right?
Yeah.
Yes.
All right. Opposite reciprocals is what you need to remember. Now, the book only does 2 examples, and somehow you're supposed to be geniuses after 2 examples. So we'll do more than 2. Determine. Well, that's really bad. How about determine? Determine the slope of a line parallel to a line that intersects these 2 points. Well, how in the world do I figure that out? Well, I don't know what the slope of the first line is, but I do know 2 points on the line, and that's the key here. If you're given 2 points on a line, then you can determine their slope simply by using the slope formula. The key here, remember, step number 1 is to always label. It doesn't go x1, y1, or x1, x2. It goes x1, y1, x2, y2, and then we plug those values in. So that would be 3 minus minus 1 over negative 3 minus 5. Stop me if you're lost. Two negatives turn into a positive, so that's 3 plus 1, which is 4 over negative 8. So we get what? Negative a half. That's the slope of the first line. Except the question doesn't say what's the slope of the first line. It says determine the slope of a line parallel to a line. We know that all parallel lines have the same slopes. So any line parallel to this line must also have a slope of negative a half. So you're actually done in one step. Parallel lines are the easy ones, right? Meaning that all you have to do is calculate the slope of one of the given. Oh, that bothers me that it says determine. And why? Both of my questions say the same thing, determine. Determine. Why isn't it an underline? All right. Next one. Okay, so that's the example for parallel lines. Let's look at the example for perpendicular lines. It's the same question, right? But it says determine the slope of a line perpendicular to the one of that given slope. Well, same process again. We find the slope of the given line. The given line goes through point S and point T. So we find the slope of that line first. Remember, it goes x1, y1, not x1, x2. x1, y1, x2, y2. 3 minus minus 1 over negative 3 minus 5. We just did that one. We know the slope was negative a half, but you got to be careful. The slope of a perpendicular line to this, can we draw real quickly? Could we draw, let's see. If it has a slope of negative a half, that means it's down 1 over 2, so it kind of looks like that. So a slope, one that's perpendicular to that would look something like this. It would form a right angle. We can clearly see that the slope would be positive. All right, so how do you find an opposite reciprocal? Once again, take the opposite. The opposite of negative 1/2 is a half. In other words, we're just changing the sign. Negative becomes positive, positive becomes negative. And the reciprocal would now be to take that fraction 1/2 and flip it. So you get 2 over 1, which is just 2. So what's the slope of a line perpendicular to the given line? Well, that slope is 2. Now, remember, the theorem doesn't say anything about opposite reciprocals at all. It says that if you take the two slopes, let's see, what are the two slopes? Well, one of the slopes is negative a half. One of the slopes, why are you doing this? One of the slopes is negative a half, and the other slope is a 2. And supposedly, if we multiply those together by that theorem, we should get negative 1. And in fact, we do when we multiply them together. Do you have to do this last step? No, right? You have to create the opposite reciprocal. But if you wanted to prove that they're perpendicular to each other and you were given two slopes, then you just simply multiply them together and see if you get negative 1. If you don't get negative 1, they're not perpendicular. By the way, if they're parallel, it doesn't really matter what happens when you multiply them. It's only if they're perpendicular would you ever multiply the slopes together. All right, believe it or not, that's all they have in the book. Like, it's not even a page long. If you flip from page 535, you get this big picture of a house being built, and you flip the page over, and they don't even take up more than, I don't know, a fourth of the page, and they're done. Right, and they're immediately on to classroom exercises. So it's a very short section. I guess that's a good thing. But I feel remiss if we don't go over a few examples. McKinley, you got your book handy?
Yes.
All right. Either from the classroom exercises or the written exercises. I don't care which one you pick. Don't pick 11 on the classroom exercise because we just did that proof, by the way. Pick something.
Okay. Number 6 on the written exercises.
All right, number 6 on the written exercises. It says you have a quadrilateral. It's given on the coordinate plane. It gives you 3 of the points, and it says, well, there's an A, B, C, and D. Now, it says the quadrilateral is known to be a parallelogram. So if you know, I'll try to draw the shape real quick. If you know that you're a parallelogram, well, what do you know about opposite sides?
They're parallel.
Right, so therefore their slopes are
Equal.
Correct. So you're also given points here of -2, -6. That point. This point is 0, -8. This is 5, -3. And you're not given that upper point. I bet we have to find that out. All right. Cool. It says, what's the slope of RV? I'll make it colored. What's the slope of RV? RV is this side right here. Oh, come on, you. My computer's been giving me issues. What's the slope of this side right here? And TV. So here's the deal. You know it's a parallelogram, so what do you know about this angle right here? If it's parallel, I mean, if it's a, oh, you only know it to be a parallelogram. We don't know it's a rectangle. Aha. If we knew it was a rectangle, then we could just calculate one of the slopes and then take the opposite reciprocal. So we do not know. It looks to be about a rectangle, but we do have points here, so we simply just need to find the slope. So if we find the slope of, we'll do the short side first. Let's see, that's y2, so that's, I hate you computer today. So that's -8 minus -6. That's the y subtracted over 0 minus -2. So I'm doing the slope of the slide. It should be negative, it should be our answer, right? So let's see, -8 plus 6 is -2. And we get over a +2. So yeah, we do get a slope of -1. -1 is that slope of the blue. Let me make the other one green so we differentiate. So we'll do green, this side. So that's the other side we have to do the slope of. Well, same basic math, just using two different other points. So -3, what, -8 over 5 minus 0. Ooh, we like zeros. Slope should be positive this time. Look at the line. It should be positive. 3 plus 8, or -3 plus 8 is 5. 5 minus 5. Oh, look, we get a slope of 1. So guess what kind of shape it is? We just got opposite reciprocal slopes. So therefore, it must be perpendicular. Got to be a rectangle. And I bet, oh, and that's literally what question B is. Why are they perpendicular? Well, the slopes are opposite. When you multiply the two slopes together, you get -1, or you can say they're opposite reciprocals. C says, why is it a rectangle? Well, if one side's opposite angles of a parallelogram are congruent, therefore opposite sides are perpendicular. Or opposite angles are right angles, I should say. Therefore, you got 4 right angles. It is a rectangle. D is the hardest one. It says, find the location of the upper corner. I got to find, where is that? That's kind of hard to do. How are we going to find that?
Well, you look at 0 and -8, go back to 0, then over 2. And it's just -1, 2. Sorry, -2, 1, -1.
Well, the issue is, well, we don't know where that angle lines up. I mean, if it had drawn where it was on the y-axis, 100%, I agree. But notice it's not. So the question is, well, how do we figure out that coordinate right there?
Geometry?
A little bit of algebra. A little bit of algebra. A little bit of algebra. We could use the point slope formula, right? Except that we don't have that second point, so we can't do that. We could find the equation of the line. We could probably do that. In other words, we could find the equation of, let me draw this. We could find, I'll do it in dot. We could find the equation of this line. Maybe. Is there any other triangles we see here? Well, we can see that we have a right triangle there. Wow, that's a little bit of difficult. I'm gonna have to give that one a little bit of thought. How do we find that? I can think of a couple things. I'm trying to think of whether we've had those formulas I just mentioned. As soon as you have those, this one turns into be not too hard of an idea. How are we going to figure out where that is? Well, we know the slope is -1. So we got y, oops. We have y equals mx plus b. We know the slope is -1. I bet we could find the y-intercept. We already know that 5, 3 is on that line. So if we plug those numbers in, let's see, x is 5, so we get -5 times, -1 times 5 is -5 plus b. And we know the y value there is what, -3. So if we add 5 to both sides, we get b is equal to 2. All right, so now I have the equation of the line. So we get y is equal to, there's my eraser, -x plus 2 is that line right there. So -x plus 2, that's that line. And we know that that other point would be right there. I'm not sure I helped us out any here. I found the equation of the line, but yeah, I'm gonna have to give that one thought. How about we come back tomorrow? Computer, come on, cut me some slack here. It's like doing things on its own right now. How about we come back? We all give that one a thought, and I'll give you a better answer on Monday for that one.
Sounds good to me.
Okay.
All right, and we are out of time. We are out of time. Any questions before we break for the weekend?
None from me.
None for me.
All right. Well, I will see you guys on Mondays. Anna here?
No, just me and McKinley.
No.
Yep.
All right. Well, we'll see. If you guys want any hint on this one, I'll have this one figured out in an hour or two. Send me a chat. I'll send you a hint. Okay.
All right. Goodbye,
All right.
Mr. C.
Okay.
Bye.
Again, see ya.